Swayam Prabha. Digital India. Educated India.
One way to do that is to take three standard normals, take a random vector x1, x2, x3, where x1, x2, x3 are independent standard normals. So you will get this vector some x1, x2, x3, just normalize it by dividing it by the norm. It will give you a unit vector who is equally likely to be in any direction, and this is extremely a useful construction. This is the most common way to sample a point uniformly from a sphere, and this works in spheres in any dimension. For 2 dimension you do not need to do it, you can just take an angle that is uniformly distributed between 0 and 360, but a similar trick does not work for 3 dimensions or higher. Okay. Now something which is relevant to us, okay. This is not so popularly known. We want to study, we would like to study how is the norm of a spherical Gaussian distributed. We know fully how is each component of a spherical Gaussian distributed. Each component of a spherical Gaussian is a standard normal, right, and components are independent, but we would like to study how is the norm, or if it is easier to analyze, how is the norm squared of the spherical Gaussian distributed. Okay. This is where our addition of multiple random variables will come in. Okay. In between I said that what are the random variables which have very good concentration, those are which arise by adding together a lot of smaller random variables. Okay. So here also you will see a similar pattern. Okay. So this X that we have is a d-dimensional spherical Gaussian, each component being standard normal, independent, all components are independent. What is its norm squared? It is x1 squared, the definition of norm squared, right, x1 squared plus x2 squared plus etc. xd squared. Okay. So this is not sum of d Gaussians. If it was sum of d Gaussians, I can finish the talk in another 5 minutes. Why? Because it is going to be another Gaussian, but it is the sum of d squared Gaussians. Squared Gaussians are far from being Gaussian. In fact, they never take a negative value. Square of any random number will not, any real number will not be negative. So this is not going to be a Gaussian, it is going to be something else. In fact, it has a name, it is a very famous distribution. It is called the chi-squared distribution with d degrees of freedom. Okay. If you add up d squares of d standard Gaussians, what you get is named as a chi-squared distribution, but that is only a name. You do not really understand anything by giving it a name, but I still put the name so that you can search for this distribution. So when you are faced with a new random variable, often the most easy statistic to study is its expectation, its mean. So let us start with that. Okay. If you analyze what is the expectation of this norm of x squared, which I represent as y, another random variable y, that is easy because it is a sum of something, and expectation has this property called linearity of expectation. Expectation of a sum is just the sum of expectations. So use that, you can represent this expectation of y as e of x1 squared plus etc. Now what is e of x1 squared? E of x1 was the mean of the standard normal, which is 0, but I am not asking what is e of x1. What is e of x1 squared? Anybody? I already got one answer, but I want you to think, this is critical. What is e of x1 squared? It is called the second moment, but in this particular case, since the mean is 0, it is also equal to, this is also equal to e of x1 minus mu1 square, right, mu1 is 0. Now do you realize what this is? This is the variance. We already know what is the variance because it is a standard Gaussian, its variance is 1, right. Same thing with e of x2 squared, it is a second moment, but since its already mean is 0, it is the variance, so it is sigma 2 squared, which is also 1. So all these terms are 1, you are adding up 1 d times, so you get d. Okay. So this norm squared of the spherical Gaussian, we do not understand it yet, but we know that its mean is d. Okay. Its expectation is d. So if you add up d many squared standard Gaussians, you get a random variable whose mean is d. You also know that it is a positive random variable or a non-negative random variable, because you are adding squares of real numbers, it will never be negative. Okay. So, if you guess, okay, now the picture here surely uses more information than what we have derived, but this is roughly going to be the shape. Okay. It is not a bell curve, it is not that I could not draw the bell curve neatly and so it turned out to be like this, no. It is something which is limited onto the positive side, its mean is approximately going to be around the d mark, if you are adding up d squared Gaussians. Okay. Now, for almost every application of this that you would have seen in this algorithms designed using random variable, once you study the mean, the next important question is to study how is this random variable concentrated around the mean. Okay. So, here I will not prove it, but we will use this result. Okay. So, we already know the name of this resulting distribution chi-squared with d degrees of freedom, we know its expectation which is d. What I am interested now is to quantify the fall, quantify the slope of this curve, quantify how fast this distribution tapers down once you move away from the mean, or equivalently how much of the probability is concentrated in a small window around the mean. Okay. So, there I will, without proof, I will use this inequality. Okay. This is very much in spirit, in notation, it is very much like the Chernoff or the Hofding bound that you have seen. You see an exponential decay on the right side, and what you are studying is also the same. The let me read it out. Okay. Probability that the magnitude of y minus d, so you expect y to be around d, okay, and magnitude of y minus d is because you consider deviations either to the left of the mean or the right of the mean as the same. So, that is why you put the magnitude of y minus d to be larger than something. Okay. That probability is going to be smaller than something. This is how every concentration bound will be stated. The probability that the magnitude of your deviation from the mean is larger than something is going to be smaller than something. Okay. So, here and then what this larger than what, smaller than what, all depends on how you do the proof for this. Okay. So, in this case, the particular result that we will need is that the deviation being larger than some epsilon times d is going to be upper bounded by 2 times e to the power minus epsilon squared d by 8. Okay. What is key thing is that there is an e to the power there. Okay. That is the exponential decay, that is why we call it Chernoff like or Hofding like. If it was only some 1 by some quadratic, then we will call it Chebyshev like, right. If it was just 1 by some linear term, we would call it Markov like. This is exponential decay, so we call it Chernoff like. Okay. In fact, if you do a small substitution, if you replace epsilon with something like beta over square root of d. By the way, I did not tell you the standard deviation of this random variable, this chi-squared with d degrees of freedom, happens to be square root of 2d, okay, or rather the sigma squared of y, it happens to be 2d, or the standard deviation is square root of 2d. Why did I say that? Usually we study concentration in steps of standard deviation. Okay. We are talk about with, if you move 2 sigma away from the mean, then how much does the probability fall. So, that is why the correct window size for studying concentration is always the standard deviation, not the variance, okay, the square root of the variance. So, here like if you are really doing statistics, you would not be bothered about a epsilon d kind of variation, you would rather be bothered about some constant times square root of d variation, because the standard deviation is like square root of d. So, that is why I have rewritten the same inequality in the here. So, by just a mere substitution, if I substitute epsilon to be some beta by root d, okay, then what do I get? If I plug it in, this epsilon d becomes beta times root d. So, it is some beta times the standard deviation. Okay. I could have used 2 root d here, but yeah, then I will have to adjust this something here. Okay. But then that is only a constant deviation, so do not worry about that. So, some beta times order of standard deviation falls like 2 to the power e raised to minus beta squared. Okay. So, 10 times the standard deviation would be like 2 to the power e raised to minus 100 by 8. So, this is the way to remember, like I mean if you need a qualitative picture of concentration, the picture that you should have in your mind is, if you move some beta standard deviations away from the mean, how much does the probability fall. Okay. So, here it falls exponential in beta squared, which is really good. Chebyshev would say you will fall like 1 by beta squared, which is not that good. Okay. We will use the green version for our purpose. Okay. It does not give that much of a qualitative understanding, but that keeps the computations simpler. Okay. So, as I told you, it is a Chernoff-Hofting norm. Okay. And by the way, we are still studying the square of the norm. You can also study the norm itself. It will be the square root of a chi-square distribution, slightly more ugly behaved. Its expectation will not be exactly square root of d. Okay. In fact, the fact that a square of a random variable has expectation d does not mean its square root has expectation root d. Okay. Otherwise, you would not really study a second moment, right. Your second moment would be square of the first moment, which first moment is the expectation. But it turns out that if you study the norm, I think its expectation of norm of x is, if I remember correctly, it is roughly square root of d minus 1. Okay. So, there is an additive error, but it is roughly like square root of d, and you can have a similar concentration result for directly the norm, and that is known by a famous name. It is called the Gaussian annulus theorem. That is because you are talking about a spherical Gaussian, and you are going to say that the norm is concentrated around d, which means, again imagine the 2-dimensional Gaussian for now. If the norm is concentrated around d, that means this distribution has its maximum probability on a circle whose radius is not d, circle whose radius is root d minus 1. So, that is like a ring around a circle whose radius is root d minus 1. This ring is called an annulus. So, that is why it is called the Gaussian annulus theorem. Most of the probability of a spherical Gaussian is concentrated on an annulus whose radius from the center is like root of d minus 1, and this is true. D here is the dimension. Okay. So, for 2 dimensions it will be root of 2 minus 1, root 1. It will be around the unit circle. For some 100 dimensions it will be more like a annulus in the 100 dimensional space whose radius from the center is around 10. Okay. So, we are going to roughly make use of this to finish our analysis. Okay. So, back to our random projection. Okay. So, this was our digression. We recapped the 1-dimensional Gaussian. We said we will restrict to the standard Gaussian, 0 mean unit variance, and then we stacked some many of these independent Gaussians to get a Gaussian random vector, gave it a name called spherical Gaussian, and also kind of saw why it is called a spherical Gaussian, because its probability density function has a spherical symmetry. You rotate it, it does not change. We know that its expectation is going to be the squared, and then we studied the norm squared of the spherical distribution. We saw that its mean is d, the number of Gaussians that you are there in the vector d, and we saw that it is fairly well concentrated around the mean. That is what we have done so far. Now, we are back to our random projections. Okay. So, remember what was our matrix A? It was a k by d matrix with each entry being a standard Gaussian. So, each row you can think of as a d-dimensional spherical Gaussian. Each column you can think of as a k-dimensional spherical Gaussian. Okay. We will use the first picture. We will think of each row as a, let me see. Okay. We will see which picture we will use when we get there. Okay. And the mapping that we are going to do, f is nothing but multiplication of your vector with a and then a scale factor, okay, that 1 by root k scale factor. Okay. Now, what we have to show is that pairwise distances are preserved, approximately at least. But now let us simplify the problem a bit and focus and ask this question, take some arbitrary vector x, okay, and now under this projection this x will go somewhere. How does the length of this new vector compare with the old vector? Okay. So, think of this x as a candidate for one of the n choose 2 pairwise vectors. The analysis is going to be the same for each of the n choose 2 pairwise vector, but now we are going to keep things simple. We are not going to worry about all the n choose 2 pairs. Pick one such vector, maybe it is the difference between x2 and x1, okay, that is what I call as x. Okay. So, imagine a single vector x and we are now going to study how it is going to behave after you do this mapping. Okay. What do we ideally want to show? We want to show that the length of this vector is approximately preserved by this mapping, or the length squared of this vector. Since it is easier to analyze, we will show that the length squared of this vector is approximately preserved under this mapping. What do you mean by approximately preserved? If norm x squared was the original length squared, after you do the mapping f of x and take its norm squared, the answer should be within 1 minus epsilon of the original length squared and 1 plus epsilon of the original length. Okay. This is an interval. What I have written with this square bracket is the interval, like we write the interval AB of real numbers, right. All numbers x which are between a and b. We want the length squared of the mapping to be within this interval, 1 plus or minus epsilon multiplicatively away from the original length. Okay. That is our aim. Now, to keep our notation simple without any loss of generality, we can assume that x is a unit length vector. That is the advantage you get because you are only targeting a multiplicative approximation, because also remember that your Ax is a linear map. So, if instead of x, if you replace it with some 10x, just that the answer is also going to be multiplied by 10, the answer will be 10 times f of x. Okay. So, you can just focus on unit length vectors and later scale it to the vector that you need. So, if you are studying a unit length vector, assume x is a unit length vector, what is the allowed range for now f of x norm squared? It is 1 plus epsilon times norm x squared, which 1 minus epsilon times norm x squared, which is 1, comma 1 plus epsilon times norm x squared, which is also 1. Okay. So, every unit vector you want to be in this interval, 1 minus epsilon to 1 plus epsilon. If every unit vector falls in this interval, every vector will fall in this interval because it is only a scaling up. F is a linear map, 10 times f of 10x is equal to 10 times f of x. Is this small assumption clear? Okay. Yeah. So, restating what we are going to do, we are going to study the case of what happens to this projection for a unit vector x. X is a d-dimensional vector and it is a unit vector. Okay. Okay. Now, it is time to use our matrix views and so on. Okay. So, buckle up. Remember f of x is 1 by root k times a times x. Okay. So, now I am imagining a as a stack of rows. That is my freedom. I can imagine it as a pile of columns, or as a stack of rows. I am imagining it as a stack of rows. I am calling them a1, a2, etc., ak. X I am retaining as such. Now, it is a matrix vector multiplication. We have multiple ways to view it. I will use the view wherein each entry of the result is treated as an inner product of a multiplication between a row of A and X. Okay. So, the first entry in the answer is going to be the first row of A, which is A1 inner product with X. The second entry in the answer is A2 times inner product of X and so on. 1 by root k I have not touched, the scale factor is as it is. Okay. Now, let us focus on one guy here. What is this A1 inner product with X? Okay, I am just expanding out the inner product here. A1x is A1, remember, is already a vector. It is A11, A12, etc., A1d. So, okay, why did I write k? It should be d, right? Yeah, sorry. This is correct. This is 2 only. This should be d. Yeah, because this is a k by d vector. Yeah, that is the only place I have to correct. Okay. I am just expanding out the inner product. But now let us interpret that inner product by thinking what these guys actually are. What is x1, x2, etc.? What kind of objects are they? No, x1, x2 are not even random variables. It's a particular, it's a component of a particular vector we chose, right? These are just components of a unit vector, right? In the previous slide, remember x was just a vector. It's an arbitrary vector. We are studying what happens when an arbitrary vector is projected using this function f. So x1, x2, xd are just real numbers. They have one good property that if you square them up and add, you will get 1. Other than that, these are just a set of real numbers with that property. So x1, x2, etc. are real numbers, scalars. Whereas what are a11, a12, etc.? Yes, they are entries from this matrix. And how did we create this matrix? Each entry was a standard Gaussian. So a11 is a standard Gaussian, a12 is another standard Gaussian, in fact independent of a11, because all the entries in this matrix were independent Gaussians, right? Similarly, a1d is also an independent Gaussian. So what is this whole sum? Yeah, in fact, it's a linear combination of independent Gaussians. And remember, that was one of the key properties I kind of emphasized to death, right? Linear combination of independent Gaussians is also a Gaussian. So this whole inner product, this guy that we are studying here will also turn out to be a Gaussian. We have to analyze what is its mean and what is its variance, okay, but it will be a Gaussian. Now, what is its mean? It's easy to calculate. It is just use the linearity of expectation, right? Your E of this guy will be just E of this guy, which the expectation goes inside the sum because of linearity of expectation. So it will be x1 is a scalar, so this will be x1 times E of a11 plus x2 times E of a22. Remember, x1, x2 are not random variables, okay? xd times E of a1d, right? Now what is E of a11? 0, because it's a 0 mean Gaussian. E of a22 is 0. So this whole thing boils down to 0, okay? So the resulting Gaussian's mean is 0. Are you with me? Okay, you are adding some 0 mean Gaussians, the result is also going to be 0 mean. Now let us calculate what is the variance of this resulting Gaussian, okay? So here, okay, I should have probably mentioned it. If you add two random variables, the variance necessarily does not add. Okay, for example, if it is the same random variable, if you add x to x, you get 2x. What is going to be the variance of 2x? It is 4 times the variance of x, not 2 times the variance of x. So variance in general does not add up, but if the what you add up are independent, then variance adds up. Okay, it is easy to show. I mean, you just write the formula for variance, right? I mean, let me assume 0 mean so that it is easy, right? So sigma squared of some x plus y will be expectation of okay, which is expectation of x squared plus y squared plus 2xy. I am assuming Ex is equal to Ey is equal to 0, which is the case that we are considering. So this will be E of x squared, which is sigma squared x, plus E of y squared, which is sigma squared y, because they are 0 mean guys. E of x squared is its variance, plus 0, because twice E of xy, since they are independent, only because they are independent, we can write it as Ex times Ey, both of them are 0, okay. So variance will add up for independent random variables, not in general, but thankfully our Gaussians are independent and hence variance will add up. More correctly, for variance to add up, you do not need full independence, pairwise independence is enough, okay, but we have more than that. So variance will add up, right, but now what do they add up to? What is the variance of x1 a11? a11's variance was 1, right? If you scale it with x1, what is its variance? X1 squared. Okay. So, this guy has a variance x1 squared, the next guy has a variance x2 squared and so on. So, when these variance adds up because of independence, this is what you will get, right. So, suddenly the norm kind of comes in. Okay. This is nothing but the norm of x squared. We use this even to derive the joint distribution thing, right. And what is norm of x squared? 1, because we are taking a unit vector. So, finally, after all this thing, this is the key takeaway from this side. Okay. Each entry in this matrix is a standard normal. Similarly, the second guy is also a standard normal. Each guy here is a standard normal. Okay. So, after you do this mapping, okay, you are taking this random matrix and taking some arbitrary deterministic unit vector and you do this mapping, you end up getting a vector all whose entries are standard normals. Are they independent? You know, is there an independence between this and this and this, etc.? Think about it. What are the random variables that come together and make the first entry? They are all the random variables in the first row of A, right. What are the random variables which mix together and make the second entry of the answer? Yeah, the random variables from the second row. Are they independent? Right, because in our matrix, random matrix A, every entry there is full mutual independence, right. So, all the random variables in the first row are independent from those of the second row and so on. So, the answer that you see here, it is not just that each entry is a standard normal, they are also mutually independent. Okay. So, we are in very, very good shape so far. Okay, this is in some sense the simplest we could hope for, and all this we got by assuming that the entries in the matrix are standard normals, nothing else. Okay. So, yeah, the first line is the summary of the previous slide. This is our mapping f, A times x, okay, and the scale factor is still there, I have not touched it. I just have given a name to each entry in the result. Okay. Each of this inner product I am respectively naming them y1, y2 up to yk, right, and we already mentioned that these y1 to yk, each of them is a standard normal and also they are all mutually independent. Okay. So, now we are ready to study what we wanted to study. We wanted to study not the norm of f of x square, okay. That is what we want to be inside a window of 1 minus epsilon, and right, this is the guy that is we are studying in, right, and we hope, we wish that this is an element of 1 minus epsilon, 1 plus epsilon. Okay. Now, let me just take this root k to the other side and square it and then consider the norm, so that on the right hand side I just do not have any scale factors. Okay. Or like, okay, maybe you can do it in 2 steps. What is norm of f x squared? You have your f of x written here, right, this is your f of x. If you want to find the norm squared of this vector, it will be y1 squared plus y2 squared plus etc. yk squared, and because there is a 1 by root k scaling, the norm squared will have that 1 by k. All I have done is that I have taken the k to the left side. Okay. So, that the right side is now y1 squared plus y2 squared plus yk squared, and we already know what distribution is, right. The name of this distribution is a chi-square distribution, this time not with d degrees of freedom, because there in the primer we were looking at d dimensional Gaussian vectors. This is a k dimensional Gaussian vector, we have already projected it into a k dimensional space. So, this is sum of k squared standard Gaussian. So, this is a chi-squared with k degrees of freedom. What do we know about it? We know what its expectation is, right. Its expectation is k, the number of things you add up, but it is the expectation of k times norm of f x squared. So, what would be the expectation of norm of f x squared alone? Without the k, you can actually strike out this k and you will get a 1. Okay. We are in good shape, because I want norm of f x squared to be within 1 minus epsilon and 1 plus epsilon. The mean is sitting right at the center. okay, the expectation is at 1. Think of this interval as 1 minus epsilon, 1 plus epsilon, and this is where we would like our norm of fx squared to fall. Thankfully, the expectation of norm of fx squared is sitting right at the center, which means we are so far so good. But now we also need to argue that it is really concentrated around this mean. Okay. So, for that we are going to use this, anyway I did not prove that. By the way, the proof of this goes almost in the same way as you would prove a Chernoff bound. You will take the exponential generating function, apply Markov to the e raised to this, just that the analysis is a bit more complicated than what you will do with Bernoulli random variables. No? Chernoff, you would have probably proved it for sum of Bernoulli random variables, right? Yeah. So, this is like a sum of squared Gaussians. So, the moment generating function, the template of the proof is same, but the actual substitutions that you do will be different. Okay. So, I am copying that concentration there. The probability that this random variable k times norm of fx squared, which is the chi squared with k degrees of freedom, will deviate from its mean, which is k, in magnitude by more than some epsilon k, is at most 2 to the power minus epsilon squared k by 8. I am just copy pasting the previous thing, right. Now, I will just cancel out k from everywhere here, right. I can cancel out the k from everywhere here and I get what I am after, right. The probability that this f of x squared, this random variable that I am studying, will deviate from 1 by more than some epsilon, which means the probability that it will either go here or the probability that it will either go here or here. That is what this red probability is, right. So, this will be some random variable which may have a curve which looks like this. We are talking about this area plus this area, okay. The probability that this area plus this area, which is the probability that this random variable fx norm squared will go into that area, is at most twice e raised to minus epsilon squared k by 8. Okay. Remember that k is going to have some factor like 1 by epsilon squared log n and so on. So, this epsilon squared will soon get cancelled with the 1 by epsilon squared in k, okay, and the expressions are going to get simpler from this point onwards. Okay. But by the way, remember that whenever you do a probabilistic analysis, there is always this confusion as to whether you should keep track of the probability of the good event or the bad event. Answer is always do whatever is convenient. In this case, we are actually keeping track of the probability of the bad event. But usually when you keep track of the probability of a bad event, we keep an upper bound on the probability. We want to show that the bad event happens with very small probability. If you are keeping track of the probability of the good event, we will keep track of a lower bound. So, in this case, bad event is that the projection's length is very different from the original length. That probability is the bad event, we are keeping an upper bound. Okay. Now, remember, we are not satisfied if you approximate one length. Our claim was that we will preserve every pairwise length. Okay. So, there are n choose 2 different lengths to be worried about, but thankfully we have a union bound which is a weak kind of a bound, but its power lies in the fact that it is assumption free. You really do not need any assumption between these events to use union bound. If A1, A2, A3 etc. are some events, then the probability that their union happens is upper bounded by the sum of their probabilities, right. That is all that we are going to use. So, here how many bad events can happen? Maybe the distance between x1 and x2 was not approximated correctly, that is one bad event. Maybe the distance between x1 and x3 was not approximated correctly, that is a second bad event. Similarly, you have n choose 2 potential bad events, right. In fact, they are not independent. If you can kind of think depending on the dimension, if some very good number of them are approximated correctly, the remaining may also automatically fall in place. But we are not going to make use of any such detailed geometric argument. We are just going to say that we have to approximate not just one, but n choose 2 distances all at the same time. So, none of these bad events should happen. Okay. But what is the probability that at least one such bad event will happen? It is n choose 2 times the probability of one of the bad events. Okay, number of bad events times an upper bound on the probability of each bad event. That is what is happening here. But before you read the formula, make sure that you understand what is inside this probability. Okay, this is there exists is a union. Okay, so we are analyzing the probability that there exists at least one pairwise distance which is not approximated correctly. That is what this says, right? There exists at least one pairwise distance which is not approximated well. Okay. So, that is what we are analyzing. What is the complement of this event? Okay. This event is the event that at least one pairwise distance is approximated badly. What is the complement of that event? Yes, every pairwise distance among pairs among points in your data set is approximated well. Okay. That is our final goal. We have to show that that probability is high, but that's it's enough to show that this probability is vanishingly small. Okay, and n choose 2 I am just upper bounding by n squared by 2, 2 and 2 goes off, you will get this expression, right. Now, all that you have to do is to pick a k large enough so that this becomes very small, as simple as that, right. That is all that is left. You have to pick a k large enough so that this becomes small. How large a k should we pick? Can you try to work it out? In fact, this calculation is something you should practice. This template of using a concentration inequality and doing that has become so common in computer science. Almost every randomized algorithm, the analysis is going to involve this kind of a thing. How many storages do you need? How many different hash functions do you need? Everything will finally boil down to a calculation like this. So, first thing is that okay, k should have a 1 by epsilon square. Okay. That at least takes one parameter away from the equation. That 1 by epsilon squared will cancel with this epsilon squared that is already there, right. And you will get something like e raised to minus the remaining portion of k by 8. But if it has to be really small, you have to cancel out this n squared, right. So, e to the power some function of n should cancel out n squared. Okay. So, you can actually differentiate this and see. Should I? Okay, maybe I'll just again wait for another minute for what dependency of n do you need? Is it polynomial in logarithmic in n? Yeah, it's logarithmic in n mainly because it is above, sitting above an e, because e raised to minus log n. Think about natural logarithm for a moment. Okay, it keeps thinking simple. E raised to minus log n is what? E raised to log n is n, e raised to minus log n is 1 by n. Okay, 1 by n is a very small number, but it cannot cancel n squared. So, what should you do? You should try e raised to minus 2 log n. E raised to minus 2 log n is 1 by n squared, which will cancel this n squared, but it will still leave a 1. Probability of 1 is still large. So, let us take e raised to minus 3 log n. What do you get? 1 by n cube. 1 by n cube will cancel out a n squared and still handsomely have a n in the denominator, which is really good. Okay. So, that is what we want. We will take something like 3 log n, but since there is an 8 already there, you need 24 log n. Okay. That is what I have done here. Okay. This is the k that I have chosen. Okay. I have chosen k is equal to 24 over epsilon squared natural log of n. Okay. Again, do not think of it as any magic. If you actually substitute the expression and try, you will see what kind of bound is needed, right. So, this is where we were at the last slide. All I have done is I have substituted k is equal to this value, and you will get n squared times 1 by n cube, which is 1 by n, which is vanishing when your number of data points is very large. So, we have said that our bad event, which is like there exists even one pairwise distance which is not approximated well, is a vanishingly small probability. And okay, by the way, one thing you should have I should have emphasized earlier is that we are approximating we are talking about approximating length of this xi minus xj or its square, and similarly, so we wanted this f of xi minus xj square, right. But what we actually cared about is the distance after the projection, which is this guy, distance between f of xi and f of xj after the projection, or distance square, right, which is actually this. Okay. Distance in a Euclidean space is just the difference vectors norm square. But because f is linear, and only because f is linear, f of x minus f of y can be written as f of x minus y. So, it is enough to just analyze lengths of individual vectors, where these individual vectors are these n choose 2 pairwise difference vectors. Okay. This is minor point, you would kind of almost assume that we had already had this picture in mind. Okay. Why I am saying is that there were variants of this projection which are nonlinear mappings, but in nonlinear mappings you have to be careful. It is not enough to analyze how the difference vector gets mapped, right. It will be, you have to analyze it separately. Okay. So, don't worry too much about this. Yeah. So, this is the conclusion. We have shown that the probability that there exists even one pairwise distances which is approximated badly goes down to very close to 0. Hence, the probability that every pairwise distance is well approximated happens with very high probability, right. With very high probability, all the n choose 2 pairwise distances in X are well approximated. Why is that true? That is because measures concentrate. When you add up random variables, their probability distribution tends to be very concentrated around the mean, and we have cooked up this transformation in a way that it mimics adding up scaled random variables and so on. Okay. So, this is the last slide for today. In summary, you start with n data points in a d-dimensional space x1 to xn, and it is almost like a magician's trick. You do not even look at what is your data point, you just pull out a random mapping. How do you construct this random mapping? You take a matrix A where each entry is normal 0 1, and it is a k by d matrix, right. And the function or the transformation that you do is you do a mapping from Rd to Rk by taking x to 1 by root k a times x. Okay. This is the mapping independent of the data. And what is the guarantee that JL lemma gives you? It tells you that every pairwise distance is well approximated, or the probability that even one pairwise distances is off is very close to 0. Okay. So, two remarks before I end. As I told you, the original setting of the JL lemma in the version that Johnson and Lindenstrauss actually proposed, it was not the transformation was not created this way. It was not by taking a matrix full of standard normals. They really took a random subspace and then analyzed the projection onto that subspace. The analysis is slightly more significantly more complicated there, but you get an easier analysis here. But can you really interpret this as a projection? Is it still correct to talk of it as a projection? So, in order to be able to call this a projection, we need essentially one extra observation, which is that the rows of the A matrix that you create have to be pairwise orthogonal. They have to be orthogonal to each other, because if you remember about how a projection matrix looks like, it was some B transpose, right, and this columns of B were orthogonal, which means the rows of this will be orthogonal. Now, if you create these, each row of this A matrix, remember, is a spherical Gaussian. So, if you sample independent spherical Gaussians, how likely are they to be orthogonal? And thankfully, the answer turns out to be that when the dimension is very large, the answer is yes, where they are very, very highly likely to be orthogonal. So, the matrix A that you construct will end up with very high probability it will end up having orthogonal rows. Okay. But so the orthogonality gets at least tackled with very high probability. But now B, remember, was also orthonormal vectors, right? You needed to scale them to be 1, but this is not of a worry. Okay. Scaling is something which you can do at any time, and in fact we have already set up all the scaling so that lengths are preserved. That is not a big worry. But what is this? Who is playing the role of the second matrix B? Okay. Again, that is only a conceptual thing, right? In the sense, like when you represent it as B, you are saying that you are representing the projection in the standard ordered basis. Without this multiplication, you are still, what you are getting, remember the projection of x onto some vector space x was inner product x times b1 plus inner product x times b2 plus etc. inner product x times bk, where b1, b2, bk was an orthonormal basis, right? What is this b1, b2, b3, bk doing here? That is only kind of telling you that this is scale factors associated to this b1, b2, bk. So, if you want to get your answer in terms of the standard ordered basis, you have to do that. But if you are okay with your answer being expressed in the basis of b1, b2, b3, then the vector itself is just this, okay, just that you have done a change of basis. Okay. So, when you are multiplying with A, you can as well do an A transpose A and then say that now you have represented the answer in standard ordered basis, but you would really not want to do that. You will even have blown up the dimension back again. Okay. You would rather represent it as coefficients of b1, b2, bk. Okay. So, once more, this is not really a projection, but with very high probability it is a projection, because the rows tend to be orthogonal. Making it orthonormal is a matter of scaling, it does not really affect anything, but the representation is in terms of this the new basis for the smaller dimensional space. Okay. So, it is approximately yes with very high probability. Okay. And the second remark that I wanted to say is that we constructed the matrix using standard Gaussians. You can just use Bernoulli plus 1 minus 1. Each entry of the matrix could be a plus 1 or minus 1 with probability half each, and the independence is needed. Okay. So, this makes computation way more faster because you do not have to do any multiplication. I think Ravindran also mentioned probably, or Venkatesh mentioned it in one of the talk. Proof is more complicated because you do not have the property that linear combination of Bernoullis are Bernoullis. So, that part the proof becomes a bit more difficult, but it is also a well famous and well proved result. So, you can also use Bernoulli plus 1 minus 1. Okay. Yeah. So, that is for any questions. So, yeah, thank you for listening so well, for responding so well during all the talks.